We're going to work with graphs and symmetry, and a lot of this, some of this is pretty basic stuff, but just want to start off with an example here. We're going to have several different types of problems we're going to go through. Just start off with this. What if they give you a function or a graph like y equals 10x minus 7, let's say, and then they say, they give you a point like this, 2, 13, all right? And they say, determine if that point lies on the graph of the equation, okay? See if this point lies on the graph of this. Well, it's actually very simple. If it is a point on that graph, then when I plug this in up here, it should be equal. So let's do that. This is an x-coordinate. This is a y-coordinate. So my y-coordinate is 13. Okay, that's going in on the left. That should equal 10 times 2 minus 7. And does it? Yeah, they're the same. So this one does lie on the graph of the equation. That's pretty simple. Do I need to do another one of those? That's very easy. Now, the next thing they'll ask you to do is they will say, complete the table and graph. And they're going to give you an equation, y equals 7 minus 3x, something like that. And then they're going to give you a table like this with some values, negative 2, negative 1, 0, 2, and 3, something like that. And they're going to say complete the table. Now, I want to go through this both analytically, or also say algebraically, and on the graphing calculator, because you need to know how to do it both ways. All right, as a matter of fact, I'll probably ask you one day to do it algebraically or analytically, and then the next day I'll tell you to do it with the graphing calculator. So if I wanted to do this on paper analytically, how could I find this thing right here? Just plug it in, right? Y equals 7 minus 3 times negative 2. Be careful with your algebra. That is 7 plus 6, so that missing number right there is 13. All right, then you do the same thing with the negative 1. You would do y equals 7 minus 3 times negative 1, which is 7 plus 3, so this one would be 10, and so on. Okay? And yes, I would like to see your steps on that. How could I complete the table if I wanted to use the graphing calculator? Let's use a whole new equation. Let's say that I had y equals 4 minus x squared. And they asked you to complete that table. All right? Well, when we're using the graphing calculator, the first order of business is to put the equation into your y equals screen. So in this case, did I give you the equation? Yes, 4 minus x squared. So we want to put in 4 minus x squared. Okay? And then, just like the last example that I gave you, they were all whole numbers, weren't they? So it helps us, and this is something you need to know how to do, press the second button and then window, which takes you to your table setup. And you can see I had something else in here, and you kind of have to pay attention to that or it'll mess you up when you get to the table. So I think that last table we did maybe started around negative 2. So I'm going to go start at negative 2. The delta table is your increments, what you're going up by. Okay? So I'm going to make that 1. Okay? And then independent and dependent, we're going to talk about this independent later, But sometimes you can use ask and just put in the value that you want. We're not going to do that right now. We just want to see the whole table, so we're going to use auto. Then, to get to the table, you press second, graph, and there's my table. Okay? So that's the quick way, right? That's the easy way to fill in the table. All right? So I wanted to make sure you knew how to do that. Now, let's get back to talking about symmetry. Oh, by the way, I'm just going to complete notes here, just in case somebody's watching this. There's the table. Be nice if you could do that, wouldn't it? But there's the table, and there's all the values that you would use to fill in the table. Let's talk about this idea about symmetry. You know, there's a couple different kinds of symmetry, but essentially we like to say a graph is symmetric with respect to, that's what that WRT means, with respect to, let's just say a particular axis. A particular axis if it lays on top of itself when folded. That's kind of a, I guess, layman's or a basic definition of symmetry. We're going to talk a little bit more about it in a minute. But let's say I wanted to talk about symmetry about the y-axis. And I'm just going to show you a real quick example here. One of the most famous ones that we will talk about and break down forever this year is the quadratic. Okay? If I have what I call the granddaddy function or the parent function of the quadratic that, you know, is not shifted left or right, if I was symmetric, I can see that this thing is symmetric about the y-axis. Because if I were to fold, if this was on a piece of paper and I folded it on that line, it would lay right on top of the other side. Okay? So that's the idea of symmetry about the y-axis. We could also have symmetry about the x-axis. And I know you've seen some of this before. That's why I'm kind of zipping through it. Let's say that this was my particular function. Well, if I was talking about symmetry about the x-axis, if the blue line is my folding line, and I fold on the blue dashed line, let's say I fold it down, and I think you can see that it would lay right on top of the other graph. Okay, so that's the idea of symmetry about the x-axis. Now, what about, here's a new one that maybe you haven't seen before, symmetry about the origin. What is the origin? Isn't that the 0, 0 point? Okay. The origin is right here. Okay. So here's what I want you to put in your notes. With the origin, you have to fold twice. Okay. If you're doing symmetry about the origin, you fold twice. Let me give you an example. One of the family members we're going to learn about this year is the cubic. Okay, and that's a graph of a cubic function. So if I folded this twice, first across the y-axis, you can see that this thing would go like that. And then if I folded it down across the x-axis, do you see it would lay right on top of this? Okay, so if you fold it twice and it lays on top of itself, then it is symmetric about the origin. All right? Now, there's some algebraic tests that you need to know. you also need to be able to check for symmetry algebraically. And it's probably helpful for us to kind of see this on a graph so you kind of know what the heck we're talking about. Let's say that I had y equals x squared. Okay, that graph is the graph of a parabola. Something like that. Okay. And let's just think of the point that we get when x is 2. If I come over to 2, I heard somebody say it, 2 squared, okay, if I use y equals x squared and I put in a 2, 2 squared is 4, right? So this point, when I come up onto the graph, this point right here is 2, 4. Well, the algebraic test for symmetry about the y-axis says that if I put in -2, I should get the same thing. So if I come over to -2 and put that in, I should also get 4. And that happens, don't I? If I put in -2, if I use y equals x squared, and I put in -2 and square it, well, I still get 4. Okay? That is the algebraic test for symmetry about the y-axis. So the test here, okay, for the y-axis is to replace x with -x. Okay? Replace x with -x. All right? What do you think it would be if I was checking for symmetry about the x-axis? Replace the y with the -y. Okay, let's just go ahead and write that down. If I was doing symmetry about the x-axis, I would make these bullet points. Replace the y with a -y. All right. Now, how about the origin? The origin's a little bit more squirrely. If I wanted to do the algebraic test for the origin, then I need to replace x with -x and y with -y in the same equation. Okay? Now, by the way, I did the example with an actual number. They're actually wanting you to do it without the number. Let me come back up to this y equals x squared and show you kind of what they're wanting you to do algebraically. If I take y equals x squared and I wanted to check it to see if it is symmetric about the y-axis, then I need to do this. Replace x with -x. So you come into the equation and you replace this x with a -x. And then you do what it says to do. You square it. So if I square that -x, what's -x times -x? Positive x squared. Y equals positive x squared. And the two are the same. So we have confirmed that it is symmetric about the y-axis. So if they say, let's do an example here. Check for symmetry algebraically. Check for symmetry algebraically. And let's say they give you this function, y equals x squared minus 2. If I want to check that for symmetry algebraically, I just follow the tests. If I want to see if it's symmetric about the y-axis, then I replace this x with a negative x. And then I keep everything else the same. I still square it, I still subtract 2. And do I get the same thing? What is negative x times negative x? Isn't it positive x squared? I get y equals x squared minus 2. These two are the same, so we would say it is symmetric with respect to the y-axis. You don't even have to check the other one. Okay? Don't even have to check the other one. Now, what if I had a function like this? Let's do a second one. Y equals negative 3x plus 5. Well, if I check for symmetry with respect to the y-axis, then I'm going to replace this x with a negative x. So I'll have y equals negative 3 times negative x plus 5. So what is negative 3 times negative x? 3x. Are they the same? Nope, not the same. Frowny face, it is not symmetric with respect to the y-axis. Let's check for symmetry with respect to the x-axis. Well, so this was y-axis symmetry. Now let's check x-axis symmetry. Well, that test is replace the y with the negative y. That was hard. Are they the same? Nope. So, frowny face there. How about with respect to the origin? Well, you have to replace them both. So I'm going to replace both the y and the x with the negative. So I'll have negative y equals negative 3 times negative x plus 5. Well, that's going to give me negative y equals 3x plus 5. And even if I divided both sides by this negative, I would not get the original, because you have to divide both of these terms by the negative. So the answer is it's not symmetric with respect to anything. Okay? It's kind of like from the island of misfit toys on Rudolph the Red-Nosed Reindeer. It's not symmetric with respect to anything. One last thing. Graph with the TI-84 plus and approximate intercepts. This is one of the most important things we're going to do this year, is be able to take a graph and look for intercepts. Let's say that I have y equals x squared minus 5x plus 6. Well, the first thing you have to do is put it into the graphing calculator. So let's do that. So go back to your y equals screen, clear out whatever you had there, and I'm going to put in x squared minus 5x plus 6. And how can I get to a nice little negative 10 to 10 window? In case you forgot, you press zoom and then the number 6 for standard. And that automatically puts you on a nice negative 10 to 10 window. Now, we really don't need to be that big. You also need to know how to adjust your window. So press the window button. We don't need all those negative x's. Let's make it like negative 1. And we really didn't need to go all the way to 10. Let's maybe go to like 7 or something. We didn't need any negative y's, so to speak. So let's just make that negative 1. And now my graph is going to look, it's going to have a lot more detail. Okay? So there's our graph. Let me get this into a place where I can write on it. When we talk about finding intercepts, on this graph? We are looking for, first off, the x-intercepts. Those will always be most important. The x-intercepts are these places right here where it crosses the x-axis. The y-intercept is this place right here. Okay? So, the y-intercept, it's probably easier done with the table. Okay? Because what is the x-coordinate right here? Isn't it 0? Isn't the x-coordinate going to be 0, whatever it is? All right? So, let's do that one first. If you go back to this graph and just go to the table, and remember we already had that table set up, there it is. Isn't it 6? Okay, so the y-intercept is 6. Now, let's go back to the graph, and I want to show you how to find these the x-intercepts on the graphing calculator. Press the second button and then trace. And what we need to select is number 2, because an x-intercept is also called a 0. So if you press that, now watch how this works. That left bound is kind of messing my window. Let me go to my window for a second so you can see this better. I want to move this up. So let's make my y minimum like -5 and my y maximum +5. Let's see if that helps. Yeah, that's going to help. So now when I go second trace, when it asks for the left bound, what you want to do is move it to the left, move the cursor to the left of the 0 that we're looking at. So I'm looking at that first x-intercept. You move it to the left of it, and then you hit the enter button. Then it says right bound. So you move it to the right of it, just a little bit past it. And you'll know you're just a little bit past it when your y becomes negative. And then you hit enter. And then it's going to say guess. Just hit enter again. And there's your x-intercept. Okay? So the first x-intercept happens to be when x is 2. Okay? The first x-intercept, the graphing calculator found it out for us right here. The first x-intercept is when x equals 2. Let's do the other one so you can see me do it another time. Okay, it's the same process. Remember, you start by pressing second and then trace to get to this menu. Then you must select number 2, which is for 0. Okay, so come down to number 2, select it. And it always asks you for the left bound first. You just move your cursor until you are just a little bit to the left of it. I'll make sure I am. I'm a little bit to the left of that intercept. Press enter. Then it asks you for the right bound, so you move it a little bit to the right of it and press enter. And then it says guess. So then you press enter again. And there it is. Okay, so the other 0 is at x equals 3. Okay? And we are going to stop there for today.